back. I think maybe the YouTube thing is messing up. I don't know. Windows had a big update last night, apparently. So, always messes something up. There we go. What's up, Rampton?
How's it going?
Just Windows just deciding to just like die. Gold, you ruined my streak. I think. No. It shouldn't count. Teacup, because I think the stream just kept going. Don't worry. I don't think it. I think Twitch has a whole like if it disconnects for like 5 minutes, it keeps it going. Don't worry, Teacup. But I do need to stream on. I might need to. I'm dreading this, but I know eventually I'm gonna have to just fully wipe this PC and reload everything, and it's gonna be such a pain.
Or just honestly, just get it. How long have you had the PC for?
This install probably 4 years, I would say, honestly.
You can just upgrade your parts, then you don't have to.
Yeah, no. It should. I don't think it's a parts thing. I think this is the problem with Windows is that after enough time, there's just enough like garbage that like resides in the the registry and the whatever that eventually it just bloats and it just fucks up. And recently I've been getting this right where I'm getting these random crashes. I'm like, okay, I'm not changing anything. Like Windows is updating itself, but yeah. So it's kind of like a spring cleaning thing where you just have to wipe the whole PC is what you have to do, and then you have to reinstall it and. That's going to be a huge pain in the ass because I have so many like audio routing things and software things making this run.
Yeah.
But I'm dreading it. See, Noise says I reinstall Windows like every 2 months anyways, right? Yeah, but I don't
like every 2 days, that's right.
I know, dude, I don't want to do that. Windows 11 is the Antichrist. Oh dear. I think I'm on 10. I think I'm on Windows 10. Let me see if I am actually. Wait, how do I figure out what Windows I'm on? Is there like a command or something?
You can probably check. Yeah.
Oh, here it is. Windows. Yeah, I'm on Windows 10. I'm on Windows 10.
Yeah.
Is Windows 11 that bad? Should I not go to Windows 11?
I don't like Windows 11 as much.
Oh, okay.
It's essentially what happened is like how like one of the things that kind of tilts me a little bit is like. We need to like right click on files because like I mean this is also because I'm running 10 and my girlfriend is using 11.
Okay.
Every time I go right click on something, like in Windows 10 you have the options cut, copy, delete, rename.
Yes.
All
yeah.
All of those have turned into icons. So you just have to like now you have to know your iconography and it's not intuitive.
Yeah.
Like the way the icons are like immediately like, oh, okay, that's the copy. Well, I mean, the copy one is like 2 pages. So that
they're trying to make it like there's just some more like GUI stuff. It's just more visual than it is like text based.
Yeah, and then I have to hover over the icon to figure out what it is, and I'm like, what was wrong with text? So like,
oh man.
So,
okay.
Yeah, I don't like it for that reason. But maybe there are other advantages.
Yeah, maybe there are other ones. So I think maybe I'll do a fresh install of 10. I think maybe that's what I'll do. Yeah, maybe that's what I'll do. Do a fresh install of 10. I don't think I want to go to 11. I think because once you start going to higher versions of Windows, then some of the old like legacy software doesn't work. And I do use like some pretty like legacy audio routing drivers and stuff. Also, pen reveal. Yes. Oh, here, let me do that. Yeah. So, Noise bought me a fountain pen. Which is very cool. Look at this. I got this. Yeah, I do have it here. It's beautiful. It's cool. Noise is a nice calligraphy person. He likes nice handwriting. Ooh, look at this. Got a nice little gold pen here, right? It's kind of cool. But you can't use a pen without any ink. So I got this gold ink all the way from where do they ship this from? Rochester, United Kingdom. I don't know where that is. Where's Rochester?
There's one in New York.
Yeah, I know. There's RIT, right? Yeah. Bro got the gold ink. I did. Here, let's see what's in it. I'm curious. Ooh, packing peanuts. Terrible for the environment. Who still uses backing peanuts?
Good evening, everybody.
What's up, Hypatia? How's it going, dude? Oh man.
Anything fun?
We're so Noise bought me a fountain pen and I'm unboxing it right now.
Oh wow.
Yeah, have you ever used a fountain pen?
I have my I have a friend who has this $200 fountain pen.
I think this one was like $30 or something. The ink actually I think was $30. Oh look, Noise. It says made in the UK. Made in the UK. That's why it came all the way from England. Look at this. This is gold ink, dude. Ooh, very cool. Golden Sands. Rochester is right below London. That's cool.
I wanted to buy the large Hagoromo. That one is actually quite costly.
What is
like
that?
One piece.
It's a type of pen.
It's a chalk. So Hagoromo.
Oh, the
Euro
chalk.
one. Yeah, the Euro one is small, but there's also a large one that I think it can reduce the unwanted noise if you use it incorrectly.
Yeah, chalk has that screechiness, right? It's such a lost art, honestly. I don't think many professors teach with chalk anymore.
Every mathematician do.
Yeah, I was gonna say that all of my.
It's a big math thing. It's a math
show
thing.
up in the feedback from
Mathematicians
construction.
has this thing about it, like they have techniques. For example, do you know how to draw a dotted line with the chalk?
I don't know. I like pretend I have like Tourette's
Yeah,
or something,
the
or what is it,
Walter
Parkinson's.
Lewin.
That's not how you are supposed to do it. You are supposed to like go against with the flow you move, and then it like press against it, and then it would like you will draw the dot line as if you are drawing a regular line.
Ah, okay.
There
Look
are
up
YouTube videos about it.
Yeah, I should look at it.
Hagromomo chalk.
Hagoro here. Let's look at it. Let's look at it real quick.
I don't even know what that.
remember
Look up
people.
Walter Lewin dotted lines. So he was a professor in MIT, who like kind of made it.
Yeah,
He has it on
YouTube
YouTube or something?
I think.
The dotted
Yeah,
line
yeah.
tutorial. Here we go. All right, let's watch
Yeah.
it.
No, not him. I want to see Walter Lewin. He's like the master of it. He
Oh,
just,
like Walter Lewin. Oh, okay. Okay, here we go. This is him. This is him probably right.
there we go.
I'm the
That's
person
the
at the
man.
hospital.
One second.
He
I
does
really-
it so like he made it a
When you get
thing.
your
I don't know if whether it was a thing until because I mean he recently retired.
He was a mathematician at MIT.
Physics professor.
Oh, physics professor. Okay, here we go. Some of Walter Lewin's best lines. That's cool. I feel like I'm watching like a comedy show or something. Like what are his best lines? Whoa.
Like he just does it quick.
Whoa. Excuse me.
No,
Excuse me.
it's
The
insane.
hell? How's he doing
No.
this?
It's insane. So you want to put the chalk like perpendicular to the board,
Yes.
and then as you drag it, the friction itself make it like skip.
Oh, okay. And then like whatever like force you pull it with, right?
Yeah. So you know how when you write with the chalk, you're holding the chalk at an angle, right?
Sure.
It's not perpendicular. Like he holds it directly perpendicular, and then you have to
Apply a certain amount of pressure so that it skips. But then, so this is a cool physics problem, right? Because it's static and static friction, I guess. Right. The Rolls Royce of chalk. That's what they call this. Hagamoro. One chalk to rule them all.
Oh, these are the ones that are like smooth. Oh, okay. Yeah, it's like a kind of oily texture, I would say.
No more dusty hands. Oh, specialized coating.
Outside, there is a coating, like
Okay.
a wax coating, so that you don't get your hands on it.
Oh, it's not
Yeah.
too bad. What's this? $50 for 10 colors? That's not terrible. I mean, I don't know how much chalk goes
There's
for.
also the large one and the luminous one.
The luminous. Luminous makes me think of like a special type of champagne or something. The luminous. Where is it? Catalog.
And then another thing about that dotted line is that what if I want to draw a curve that is dotted?
Oh, you can still do it, right? You just gotta probably. I mean, man, that
Gotta
friction's gonna be
practice it
difficult.
more, I guess.
Yeah, that's really difficult.
Hmm.
Wow. Okay. Cool. Well, that's awesome. Chalk is dope. Thank you, Noise, for the gold ink and everything. I'm not gonna try to like fill the pen up here like on the stream because I'll probably like spill gold ink like all over my desk. But I will try it afterwards, and we'll see what the writing looks like.
Yeah.
All right, cool. All right, let's start off office hours. All right, welcome everyone to office hours. My name is Dr. Gold. It's Actual Education. Streamer helps you out with math homework, science homework. Joined by my awesome associate professors, Ramton and Hypatia. Love y'all. Let's see. I think the first question we had today was it Noises? Noises question was first?
Yeah, I think I was gonna do the derivation for the simple harmonic.
Okay.
And
you want to start? You want to start us off with that? Yeah, with like how the differential equation works.
It's a cool like derivation because it's simple. It's for physics and also like people learn.
Yeah, and there's some math with it, right? There's some different. Yeah.
So I guess it's kind of. Let me just open up as well. Are we on page 1 of this?
Yeah, I deleted all the other pages.
Oh, okay. Yeah. All right. So we want to do the simple. I'll do the spring one, which is the easier one. So let's say you have a spring, and then there is a mass attached to this. And so, let me do that. So, and then there is a mass m attached to this as well. Okay, so one thing, a lot of the time, depends on whether you want to do this like assuming that that you want to include the variable for the basic length of this spring or just with the extension. So let's say this extension is x, where it could be some distance away from the equilibrium.
Right. Equilibrium is the position where the spring is just chilling. Like it's
exactly.
not moving or anything.
Yeah, exactly. So it has no compression or no extension.
I think that's something most students don't realize is that like springs go both ways, right? If you pull on a spring, it wants to come back and be not as like extended. But if also you push in on a spring, it's gonna want to like push back to not be.
Exactly, and that's actually why the negative sign exists in the Hooke's law.
Yeah, a lot of people don't know that one
as well. So like, let's say if you wanted to include the length that is the equilibrium length of the spring as well, so we call it L, right? Because like this is the length in which your spring is at equilibrium. So now your force is going to be the negative K times X minus L.
And this is Hooke's law. Great old Hooke's law noise.
Yeah.
But we love Hooke's law.
So why am I calling, I guess with this one, X would be, if we are doing it with the length of this, it's going to have to be the, X is the total. I guess it would be kind of like this. This would be what we consider X, but it's also typically it's easier to just not include this equilibrium length because we just want to take this extension as a whole. So typically it's easier to just go with minus kx. Now, as I said, the interesting thing about this is the negative thing, which a lot of people don't understand why. So think about this. If the extension is to the right, doesn't matter which way you consider. Let's say this is the positive direction. Okay. Now, which way is this spring want to bounce back? To the opposite direction, right? Now, similarly, if a spring is compressed, and let's say this is its equilibrium point, and it's compressed by this amount, x, away from its equilibrium, then once again, the force is minus kx. So your x is in this direction, and your spring is compressed, and it wants to push to go back to the equilibrium. So I'm assuming noise is also here.
Yeah, Noise. Give us a pulse, dude. You hear Noise? We're doing your
Just wanna-
question.
Yeah.
Let's see.
So then that's where the negative sign comes from as well. It's the fact that the spring is always has hello. Yeah, so the spring always wants to push back essentially. That's why that negative sign comes from. So if it's an extension, it was to compress it. If it's a compression, it was to extend it. Now, from Newton's second law, we know that the force or the sum of all forces is equals to ma,
Mhm.
which in this case, it's only the kx. So now we can write this in terms of a differential equation. It's m times the second derivative of the position equals to minus kx. Now this gives you d squared x dt squared equals to minus k over m x. Now, a lot of the times people give you the solution here right away, and they call this, you're like, oh, the solution is like cosine or whatever. And so what you want to do, you can actually solve this. Again, this is a second order differential equation. It's easier to solve because this k and m are both constants. This k is the spring constant, m is the mass. So if you were to solve this, like if you wanted to know the math, once again, you solve x being e to the lambda t, and you put the whole thing on one side, so you have d squared x dt squared plus k over mx equals to 0. If this is the format that you want your x to be, then the second derivative of this gives you lambda squared e to the lambda t
Mhm.
plus k over m e to the lambda t equals to 0. Now this gives you can factor out the e to the lambda t, lambda squared plus k over m equals to 0. We know that an exponential can never be 0, which means that this is 0, which means that lambda squared is minus k over m, which means that lambda is square root of k over m I. The I comes from the fact that when we take the square root, there's a negative under there.
Yeah.
So this thing right here, this quantity, we call it omega, which is going to be your angular frequency.
Yeah.
Or sorry, angular velocity. And so now your solution, as we said, when you have a imaginary number, your solution is now e to the I omega, which is cos omega plus I sine omega. Sorry, there's a t here. And this is when you're including the imaginary parts of the solution. If you want to only take the real, you just drop the I from it. But these two are not, you have to include some kind of factors in front of these two because you want them to be any linear combination of a cosine and a sine. So your total solution, which is x, is going to equal to, would you mind just
Yeah, got you.
scrolling?
Yep.
So your total solution, which is x, will look like c1 cos omega t plus c2 sine omega t. Now, a lot of the times, it's easier to set the initial conditions in such a way so that one of these two things, either c1, I think you skipped a step. Show us how you got the exponential.
Ooh, so the wave equation?
It's up there.
That was this. Oh, sorry. That was this, right? This is the wave equation right here.
That's the wave equation. You get lambda in here, which is the lambda squared gives you lambda to the lambda squared is minus k over m.
Mhm.
And the explanation also was that e to the lambda t cannot be 0. So then this other factor is 0.
Yeah, this
which
must be
gives
0.
you lambda being equals to the square root of k over m, this square root of k over square root of k over mi. That square root, we call it omega, and then your total solution is going to look like this. And then in here, you can always set your initial conditions to be so that your what's it called? One of these two, like either C1 or C2, is equals to 0.
Right.
So one of the common practices is that, like, when we take x naught is equals to some length a, let's say,
Mm-hmm.
which is the amplitude, what we call it, and then we say that the initial point, let's say it has velocity 0, so it doesn't have any sort of it just starts stretched out, but it's not moving already.
Right.
So then what you can do is that this gives you x of 0 is equals to a. Put 0 in here, you get c1 cos of 0, which is just c1,
right,
plus c2 sine of 0, which is just 0 as well. So the c2 doesn't appear. So c1 is a. Okay, cool. Now we take x prime of t, which is going to be minus a omega, or actually,
Yeah, minus a omega cosine omega t, right? Or sine omega t, sorry.
sine omega t, yeah, plus c2 omega cosine omega t. Now, if we take its initial velocity to be equals to 0, again, once you plug in 0, the first term goes to 0, so nothing. The second term, you get c2 omega is equals to 0. Since omega we already know is non-zero, it gives you c2 is equals to 0.
Oh, that's very cool.
So now your total solution, x of t, is equals to a cos omega t, where this is your initial amplitude, and this omega, as we said, is the square root of k over m.
Oh, very cool. Yeah, I think when we learn it in physics, they straight up just tell you that this is the form of the solution. Like when we have the wave equation, like at least when I went through college and whatnot, we get to this and then we say, oh, let's just assume x is equal to a cosine omega t, and then you just prove that it is. But I like this. This is very reminiscent to what we did yesterday, or sorry, our last stream, Ramton, right?
Exactly. That's why I wanted to do this.
Yeah, this is good. Yeah, it's very related to the last thing, where like, yeah, this is a second order differential equation, and you're doing the same e to the lambda t, and then this was we have two different solutions, but the C2 ends up going away because of the boundaries on the initial conditions.
Exactly. And the thing is, like, cool. you can always write your solution. So whenever you have, this is also, you can always show this using trigonometric identities as well. Whenever you have a solution that is a linear combination of sine and cosine, what you can do is you can just write x as c1 cos of omega t plus alpha, or plus phi. So you can translate the second part into a phase
difference,
phase transition, which, again, you can expand this, right, using cosine laws, right? It ends up being like cosine of something times sine of something else
plus sine of something times cosine.
Yeah, and then so you would end up getting back the same thing.
Right.
So instead of having this, you could also only be using one trigonometric function, and then just with a phase involved in it, right?
Right. Because that's the only difference between sine and cosine, anyways. It's just a phase change. A lot of people don't get that. They're like, oh wait, well, these two different things. I'm like, no, it's just off by was it 90 degrees or 180 degrees? 90. It's off by 90. Off by 90.
Yeah.
Yeah.
And then, that's cool. Yeah. So this was for the spring. And I think I wanted to, with this one, it's a simpler one. So we show the math, we show the concept. Now I'll show the pendulum.
Okay.
And once you set it up, the rest of the problem is, again, the same thing. So
we'll put on page 2. Yeah, you got it.
Yeah. Good. So for a pendulum, it's again, it's better to draw a diagram. So let's say you have like a ceiling, You have a pendulum. I'm drawing this a little bit bigger than it needs to be. So we know that the pendulum is in equilibrium when it's just hanging from the ceiling, right?
Sure.
So what happens in here is that it's been extended away from the central line by some angle theta, right? So what I'm gonna do is that I'll have to, again, first thing we want to do is think about all of the forces that act on this.
Right.
So there is the downward force mg, and then there is this force of tension along this wire.
Mm-hmm.
Now, typically, whenever this is actually a very important thing with, I feel like there's not enough emphasis on it. Even first year, I feel like not a lot of people said how you break down like a vector to two other components.
Yeah.
Because a lot of the times it feels like, okay, we want to break things down into right, left, and up and down, right? But then sometimes we end up putting it at an angle to when will the Terney start? Oh,
Good,
is that
keep going.
different?
Yeah, you go.
Okay.
Keep going. You're good.
And then, so sometimes you end up putting in at weird angles, and the question is why? The answer to that is that whenever you're doing in physics, it's not about breaking down into right, left, up, and down components.
Mm-hmm.
It's to actually break it down into components that your thing is going to be able to move. So typically, if your object is allowed to move right, left, up, and down, you want everything to be in terms of those.
Right.
So, like, for example, a slope, your object is going to be moving this way and this way. And then this is the up and down. So those are the directions that you break it down into.
Yeah.
So this is exactly what you'll do in here too. So this thing will follow along like an arc like this.
Mm-hmm.
So you would break it down into two components, one of which is
the tangential. Yeah, the tangential, I guess, movement, right?
Exactly. And then the other one is going to be vertical or perpendicular to this.
Sure.
Which also is going to associate, I guess another way of thinking about it is better. Let me do it this way. So it's this way and this way.
Mm-hmm.
So now that we've done that, we can actually, now we can do the problem as well. So you can see this side one in here is going to counteract that tension in the wire.
Wait, which side one are we talking about? So like this is like our new coordinate system. It's something like this, right?
Yeah, exactly. Yeah.
Right.
So the one that is pointing directly in this direction.
Oh, the component of the gravity that points opposite to the tension. Gotcha.
Exactly. So this is
okay, very cool.
This is going to be equal to the tension because your rope wants to keep your object in place.
Mm-hmm.
Now the tangential one, and this is also again important in understanding vectors. A lot of the times people think, okay, the vector is here, but my motion is here, right? It doesn't matter because a vector is like a virtual thing. It doesn't actually exist.
Doesn't matter where it starts or stops. It just matters like what's the direction.
Exactly. So it's the magnitude and the direction that matters. So as long as these two things are pointing in the same direction and have the same magnitude, then it's not gonna matter.
Cool.
Okay. So from here, we're gonna have to find out this angle, so we can write these two components in terms of those.
Mm-hmm.
Now, if you look at this red line, which is the direction of mg, is perpendicular to this vertical line here.
Yeah.
And this blue one is along the direction of the string, which means that this angle is also theta.
Okay.
Does that make sense? Because
these kind of like we have like a transversal here is like kind of what we have.
Yeah, exactly.
Right, and then these are the corresponding angles.
There you go. Exactly.
Very cool.
So now from here we can write the two components of this. So this one is going to be mg cos theta, and this other one is going to be mg sine theta. Now, the tension in here needs to counteract that mg cos theta. So your tension is your mg cos theta. This doesn't give you any information, but it's cool to know, like, this is how the forces end up balancing out. Also, I think you might have to zoom out a little bit.
Gotcha. Yeah. Okay. Oh, we're down here. Got it.
There we go.
Cool.
Yeah. And so the tension in the wire is the mg cos theta. And then the mg sine theta is the driver of your motion.
This is like the Hooke's law. This is like the Hooke's law part of it, right? It's the restoring. They call this the restoring force too, right?
Yeah. I guess it would be going back to its original position, so that's why it's the restoring.
Yeah.
And so this is the mg sine theta, and this is 1 equals to ma, because this is the force, right?
Yep.
AKA F is equals to ma. So this is why the m's cancel out in this one, because last time we had kx is equals to ma. This time we have mg sine theta is equals to ma.
Very cool.
So there we go. The m's cancel out, and now in here you have to solve this. Now, as we know in here, this a is the second derivative of position, but it's equals to this angle. Now, depending on where we are, again, this position x, so-called, we call it, is going to be, it's not actually
this is a linear position though, right? Like,
yeah, it's better to actually write it this way. I'm going to call it r, because it's relative to the radial distance that it is from in here. Now, obviously, the force, what is it in here that is changing? It's the angle, right? So r in here is length times the angle, right? Which is the radial distance. At any point, I am a distance r away, and that r is equals to the length of my object.
well, isn't this kind of like r? Is this what it is? Yeah.
R would be
This is the arc length, is what this is. I think is what you're saying, right?
Yeah, it's the arc length.
Yeah, sorry. This is L.
Yeah,
right?
that's L. You're right.
Good.
Yeah,
and then
L
this
arc length is, this one is r.
Good.
Which is the distance that it is going to travel. It's the direction of the motion. Right?
Thank you,
So
B,
that
for this.
r is equal to L theta.
Yeah.
So when you take the derivative of this is where it becomes helpful to know, like, explicit derivatives as well. The L is the length of the string, so that one doesn't change. So it becomes L d theta dt, and then the second derivative of this becomes L d squared theta dt squared. Okay, so we have L d squared theta dt squared, and this side we have g sine theta. Now, to solve this is actually a difficult problem to solve just analytically, which means, like, if we want to find a function that it represents theta in terms of, like, time or something, it would be very hard to find that. So physicists come here and do a very, outrageous.
We are outrageous, honestly, as physicists. Yeah. We tend to make these, like, ridiculous, in the eyes of mathematicians, assumptions.
Yeah. So now the thing is, this is actually not that outrageous.
Sine of theta is equal to theta. Yeah, the small angle approximation. We're just like, don't worry about the sin.
Theta. Yeah. It's no. This is called the small angle approximation. Now, this works really well for your functions, and when your theta is small. Again, small depends on what you consider to be a reasonable amount of error that you would have.
How small is small? How small is small?
Yeah. So I think typically people like to say, like, smaller than 30 degrees,
Really?
right?
I thought it'd be like 5. Like what? 30 is considered small?
Yeah,
way.
like 30 degrees. It's still pretty accurate, or like 20 degrees.
Okay.
So like I would say like up until 30 degrees, probably you would have less than a decimal. You're probably going to be 1 decimal place off. So it's not a huge discrepancy
Mhm.
in terms of like the amount of error that you will get.
Mhm.
But the reality of this is that if you wanted to do this, the better
His noise is like sine of 30 is a half. That's pretty significant.
no,
It's
it's a
okay.
half, as in if you do this with a computer to find your solution, and then you figure out the position, right?
Mhm.
And then the position, if you just do this approximation, and then you do it actually numerically, the amount of error that you would get from like your position being off from where you expect it to be is going to be less
Oh, I
than
see.
1 decimal place.
Yeah, he's saying so. What once you like put it into the differential equation and solve it like
Yeah.
analytically
your
versus
solution is less
computationally, the solution is only a decimal. Yeah, because
Yeah,
you're
it's
right.
only-
Yes, sine of 30 is definitely a half. Right. Yeah.
Yeah. And if you wanted to actually do this a lot more accurately,
Mhm.
you could arguably just do this theta minus theta cubed over 3 factorial, I think.
Ooh. Okay. Taylor
This is the-
series
This is the
or Maclaurin
second,
series. Right.
it's the third order approximation.
Oh, okay.
And
Cool.
for this one, you would be able to find like a lot more accurate, and then you could also get into perturbation theory. So and at some point, I may go over this because it becomes like once you get a good grasp of differential equations, perturbation theory is not that difficult.
Sure.
It's just a bunch of algebra and stuff. So, but for now, we're just gonna stick with the first order approximation. So up until this point, this is the exact differential equation that you have. Now from here, you go to g theta equals to L d squared theta dt squared, and then now in here, if we divide by this should have been also a minus in here. Or wait,
Because the
is there a
forces. Yeah, there should be.
here, because again, the reason for this is that the direction of the increase, so you can think about the direction of the increase of your angle, is it increases this way, but your force restores it in the opposite direction. So as your angle, you can think about this g sine theta term. As theta increases, what do you get closer? This gets bigger and bigger, right? And the bigger and bigger it gets, the more force you're going to have being applied to this. So that's why it's important that we put the minus in there, because it's the direction of the force matters. So anyways, we come back in here, you are essentially back into the same differential equation as you started. So now I can have g minus g over L theta equals to d squared theta dt squared. And now here, you can see your theta is going to be, as we expected, like, let's say initial
Same
condition.
thing. Yeah.
We're going to take the same initial condition. X of 0 is equals to a, which is your amplitude.
Mhm.
X prime of 0 is equals to 0, so it doesn't have any initial velocity. You can get theta is equals to cos omega t, where your omega in here is the square root of g over L.
Yeah, very cool.
So this is the same differential equation as last time, essentially.
Mhm.
You
And
know,
this is
that's why-
and there's a cool thing to this, right? Because omega, some of the kids here are probably like, what the fuck is this W thing, But omega refers to like how fast this pendulum is like swinging back and forth, right?
Yeah, exactly. So the bigger the omega, so typically you can think of it this way. In order for a cosine to kind of just make like one cycle, right?
Mm-hmm.
So this is, I guess it starts like this and it goes like that, right? So it goes from 0 to 2 pi, right? Or you can think of it as the entry of this goes from 0 to 2 pi to make it one cycle.
Yeah.
So now let's assume that omega is 3. So let's think what happens to omega. Omega, if it's a cosine of 3t, if t is 0, this gives you cosine of 0, which is the starting point.
Mm-hmm.
But if you want the outcome of this to be 2 pi, then what should t be? T should be 2 pi over 3.
Yeah.
Because that 3 is gonna is essentially shrinking this. So what happens is that instead of this cycle happening from 0 to 2 pi, it would happen from like 0 to 2 pi over 3. And then that's why we call this the period of this, which is t, is going to be 2 pi over omega all the time. So if the omega is 1, well, it's just 2 pi. If t is a different number, then or say if omega is a different number, your thing is going to be 2 pi over. And then if they ever ask you for the frequency is 1 over t, so it becomes omega over 2 pi, which is, I think, one of the questions where they ask you noise about the frequency, or I don't remember if it was.
I'll pull it in. Oh, amplitude and frequency. Yeah, that's what it is. Here it is.
So
this is it.
Yeah. So in here, where they ask you about the amplitude, so the amplitude is the number in front. This is how much up and down it goes. So if you have,
you got it.
Like x, it does like this distance, like, or I guess the maximum. And here, that's your p, which is your amplitude, and then it goes to minus p from the other side. So you're between b and c already. Then the next part asks displacement t given, what are we asking for? A frequency. So frequency, remember, is 1 over t. T, which is the your period, is 2 pi over the factor in the cosine. So it would be q. So therefore, if they ask you for frequency, you just have to flip this. So q over 2 pi. So then you are left with...
I love how they use q. Like, trying to say, oh, it's a little cutie. What's the cutie? What's the cutie in the cosine? Yeah, this is cool. The other thing I wanted to like kind of like point out here was so when we figured out right here that so we have two different cases here, right? In the terms of like springs, right?
Yeah.
Omega is equal to the square root of k over m, right?
Yeah.
And in the case of pendulums, omega is equal to the square root. It's g over l or l over g? I always forget which one. I think it's g over l.
I think it was G over L, yeah.
G over L, yes. What's really cool with pendulums is that the amount of time that it takes for this thing to swing back and forth is independent of the mass. There's no mass in there.
Yeah.
So it doesn't matter if you have a bowling ball or a marble on the end of a pendulum. The amount of time it takes for it to swing back and forth does not care about the mass. All it cares about is what's the force of gravity, which depends on what planet you're on, and then how long your string is. Which is very cool.
Exactly. So I'm gonna I'm gonna put up a picture also here.
Sure. Yeah, put it up. Yeah, I got you. Let's go right there. Ooh, okay. Is this a phase diagram? What do we got here?
Control S, was it for selecting?
Yeah, S is select. Yeah.
Oh, just S. Okay.
Just S.
Oops. So here, maybe. So okay. So in here, noise, you can see these lines that are in the middle. So this is called a phase portrait, which is, this shows your, you don't need to worry about this too much for now, but in here it shows your momentum, right? But instead of momentum, think about velocity. And here it shows your position, right? So if you had if your solution was just as we expected at like cosine, it's just it's going to go exactly between sine and cosine, right? Because your position is going to be something in terms of cosine, and then your velocity is going to be something in terms of sine. So it's going to go back and forth between the two. So you expect it to be circular. Now you can see that the inner circle, or the inner phase portrait, the inner they call it path. It's called the something path. Anyways, this one is pretty much circular. As you start to increase your angle, so this is the angle as we called it, right? So you see in here, that's the 2 pi. You can say that's your starting position, right? In here is probably like, a little bit more than over 2 pi. And here is a little bit less than 2 pi. So let's say this is pi over 3, which is like 60. It seems about that. It's already pretty accurate. It's very circular. So once you start to get a little bit bigger, like let's say 2 pi over 3, that's when you start to see some bulging in this, where it turns from circular to kind of oval shape, right?
Oh, so the solution, this is why the small angle approximation starts to screw up?
Yeah, so you can see this one, the inner one is still pretty circular.
Yeah.
Right? Because the phase portrait essentially is the ratio of one to the other.
Sure.
And so remember, omega in here is square root of k over m. Anyways, I'm not gonna go over it. This is gonna be really good.
Yeah.
It's gonna be a shit show too.
No, it's okay. Yeah.
But yeah, a lot of the times what you want to do is like you scale this a little bit, but you can see that x squared plus x prime squared is equals to 1, given that you scale this by the right amount, right? So what you would do if you scale this by omega, you can end up getting x squared plus x prime squared equals to 1, right? So it's going to be a circle.
This is the equation of a circle.
The equation of a circle, yeah. So for an oval, it's going to be a little bit off as well. So it's going to be a little bit more oval shape, which even for this one, it stands a little bit more true.
Right.
But then past a certain point, you're no longer going to get these. So the small angle approximation, even your math wouldn't add up.
Like there's no solution if you're going all the way to pi.
Yeah, once you go to pi, it's going to be...
At that point, the pendulum's like upside down, right? You're just like way up here.
Yeah. So once you have more than pi, you essentially are like swinging it.
Yeah.
In the opposite direction. So it's
right.
So it's like starting in this, but instead of falling this way, you're pushing it this way. So it's going like this. And so it's going to kind of start to go around and around and around. Now this is given that your pendulum doesn't have any damping. When you do have damping, I'll post.
Yeah. Okay.
Here.
Damping is like friction or like air drag or
yeah, exactly. Because you have a pendulum, it's gonna have some friction in the
in the string, and you put on the bottom there.
Yeah.
Okay, cool. Whoa, yo, this is trippy. What is this?
Yeah, so for this one, you can see that your path starts to kind of spiral in, right? So when you spiral, instead of coming back to the same spot, so let's say I'm here.
Yeah.
When you spiral, instead of coming to the same spot on the other side, I've come in here. Right? So I've gone closer to the center, which kind of makes sense because the pendulum kind of swings like this, and then it goes less back. compared to the last time. So it goes like this.
You've seen the classic video, right, of someone, like some teacher, like standing on a chair with a massive, like, bowling ball, and they say, I'm going to let go of this, and it's not going to hit me, because I trust in the law of physics.
Yeah. That's Walter Lewin also.
Oh, is that also him? Oh, that's so cool.
Like the one that he says, if it hits my face, I'm going to die, and then he just swings a thing across.
I'll find it. You keep going.
Yeah. So this is the whole point of I guess this is where the damping comes in. And, in case you're interested, the damping one is going to be, your equation looks like this. MA, which is your force, is equals to minus KX. Okay, great. And then there's going to be a minus B times V. Because whichever the direction you're moving, whatever your velocity is, there's going to be a backwards. So if your velocity is going in a certain direction, the drag is always going to be in the opposite
of
direction.
the movement. Yeah, it's like friction always opposes where you're trying to go.
Exactly. Hence the minus, and the B is just some factor that is based on the coefficient of friction or like
sure.
Stuff. So then this is once again becomes a second order differential equation, which you can solve, but
Very cool. Here, let me put the Walter Lewin video up. This is a cool one for the kids to kind of see. And this is kind of more like conservation of energy and stuff, but it's still cool. It's related to the pendulums. See this guy.
A pendulum.
I
have an object that weighs 15 kilograms and I can lift it up 1 meter, which I have done now. That means I've done work. MGH is the work I have done.
Yeah, where's MGH? Here we go.
They use these devices. It's called a rack.
I don't know if your stream is really behind on
Twitch. It's probably like 5 or 10 seconds behind. Yeah.
Into
Here we go.
Kinetic energy, and that way you can demolish a building. You just let it hit.
Ooh.
And it breaks a building. And that's the whole idea.
Yeah, so with that one, he gave it some initial force.
Yes,
So
he gave it some initial velocity or something.
Conversion of gravitational
Let's see the one where like he almost like breaks his. This is it.
Yeah, so he has to let it go without giving it any push.
Any force, yeah, because if he pushes it at all, he's screwed.
Yeah.
So that when it comes back, it may touch
So
my
he needs
chin,
to let go.
but it may not crush my chin.
It's just.
This is where like some kids like blowing like at the front of the class going like.
If I don't succeed in giving it 0 speed, then this will be my last lecture.
He was really famous for doing a lot of like
close my eyes.
experiments
I don't wanna
that
see this.
had some kind of
So please be very quiet.
demo, I guess.
That's so cool. I love the physics
I
demos.
almost didn't sleep all night. 3, 2, 1, 0.
Oh my god. I'd be like, no,
It's a big swing.
What? Look at this. Just. You imagine you see this like massive 55 kilogram like ball coming at you. You're just like, okay. How much do I believe in the Matrix? Are the physics laws? Are the physics engines working today? Very cool. All right, that's dope. That was cool. That's cool.
Yeah, nice. Hopefully that was
Informative noise.
Yeah.
You learned some stuff, noise.
I went over because like I think the derivations of these are very cool. Like I actually didn't like a lot of the times when I'm in math classes, they don't care about explaining the physical aspect of it.
Right.
And if I'm in a physics class, they don't care about explaining the math class.
Yeah, exactly. I liked how you went into a lot more of the math here than I'm used to like seeing when they do this derivation. And it's cool to see, yeah, they're best buddies. Math and physics are best buddies, This was especially cool. I liked it because this also very much applied to what we did on Monday. I was like, oh, okay, cool. This is why differential equations apply to like real life. Very cool.
Exactly.
Nice. Awesome. Thank you, Ramton. That was really cool. Hope everyone else we had like 11 viewers like peeking there at one point, so that's cool. People probably a fan of it. Let's see. Next question up. Ethan, are you here, Ethan? We'll get to yours. Where's noise? There's. Oh, and then there's Ethan. Ethan's coming in, and then Teacup. We're gonna do yours next. Okay, so Teacup. soon. All right, let's see. Ethan, what's up, Ethan?
I'm fine.
Did you see some of that? We were doing some physics today. Did you see the physics we were doing earlier?
Not really.
Oh, not really. Okay. Well, it'll be there later if you want to see it. I know you're learning a little bit of kinematics with Noise in the Discord. And we kind of went over a little bit more advanced types of physics, but it's still related. It's the same kind of. But okay, let's see. What are you doing? Ooh. Okay. I like this uniform acceleration. Bum, bum, bum. It just struck 1 a.m. Good job. It isn't this time last week. Yeah. All right, cool. A bike accelerates uniformly from rest to a speed of 7.1 meters per second over a distance of 35.4 meters. Determine the acceleration of the bike. Yeah, this is a good one. You know how to do this one, Ethan?
I mean, if I remember the formulas, then yes, I can do it.
Good. Okay. What are the formulas? Let's. These are one of the things where you will get a formula sheet a lot of times in physics, but it's pretty useful. These equations you use like over and over and over again, so it's almost like worth it just to memorize it. And actually, if you really get lost, you can use calculus to rederive them if you really wanted to. But okay. Let's get a screenshot of what like a physics equation sheet would probably be. Like on an exam. You know what? Actually, okay, here we go. AP Physics 1 equation sheet. Let's see what like College Board would give you guys as an equation sheet. Like an image. Please have an image of it. I want a big image. Where's a big image? No. This is pretty decent. There we go. Copy this. Okay, cool. All right. So, Ethan, when you take AP Physics and whatnot, this is probably like the type of equation sheet that you'll get, okay? You see how like there's a ton of stuff on this, right? Kind of scary, right?
It doesn't tell me how to know all of this.
Well, you don't have to know all that. I mean, this is to like help you, but if you go through a whole physics class, you will have used every single one of these equations. And some of this stuff is just kind of like useful. Like here, see how they have the Pythagorean theorem here, right?
Yeah, I love that. I love that formula.
Yeah,
as
these
long
are
as tangent.
right, okay. And then these are, for instance, the areas and circumferences and volumes of different shapes, right? This is electricity, so we're not doing electricity right now, so you don't need to look at that, right? What we're doing when we deal with things just moving and whatnot, that's what we call mechanics, okay? You can think of things like mechanical. Things are like moving around and whatnot, okay? So these are probably the equations you're going to want to use.
I don't even know any of this. I thought we were just gonna use like the five equations that I know.
Good. We are. But I'm showing you where to find them. So when you take a test, Ethan, they're going to give you an equation sheet with a lot of equations, and it helps for you to know where to look to get the equation that you need, right? I'm just showing you that, like, we want to start looking at mechanics. You'll notice that, like, ooh, here's some stuff that was related to what Rampton was just doing. Like, this is like the spring stuff and the pendulums. But for our case, like the simple stuff, like things just moving and whatnot, these three equations are the ones that you're really going to use, okay? We call these like the kinematic equations. Or as Noyce likes to call them, SUVAT. Like that, yeah, kinematics. Okay?
Okay.
Does that make sense, Ethan? Like, those are the ones we're going to use? All right, so
It doesn't really make much sense to me.
Pardon?
It doesn't make much sense to me.
Okay. What doesn't make much sense about these? These are the equations you've seen before, right?
Well, they're not in their exact form. Like none of these should match 5.
Yes, there are another 2 that are kind of basically derived from this, so that's why they don't write them, because you don't really need to know them. Like they're based on that one. It turns out, Ethan, you can solve almost all kinematics equations just by using these 3. Yeah, Noyce says these look even worse. I know, but this is what College Board gives you. So like this is a real example of what like a college credit course exam would be. This is what they would give you. And so it's important to be able to know how to adapt to that equation sheet and know how to read it.
At least, can I not use it now because I'm not even taking physics right now?
Yeah, I know. Well, you know, it's this isn't too bad. Here, these look like the same equations, right? What's different about them?
It's like they're not like when I'm looking at the second one, it doesn't have like a VI in it.
Good. Okay, so here, let me teach you this because this is the thing they do in physics. Okay, VI. Sorry, let me get the font here. So you can either refer to things as, for instance, like VI and VF, right? You learned this, right? VF and VI, right? Where this is the initial and this is the final.
This is no, I already know this.
Good. Initial is the same thing as saying V0, is what they say. They call this like V naught. It means like it's the zero. It's the initial one. Okay.
Then how is that gonna relate to that? How are you even gonna fit that?
Well, so instead of V naught is basically the same thing as saying VI. Okay.
Okay, but what about VF then?
That's basically just V. In this case, these are all just, if you see the letter by itself, that's the same thing as the final. Is what they mean. Okay.
Okay.
Okay. It's I know this is new to you, but this is an important thing because just like you know, like even just with speaking, right? If you go to different parts of the country and whatnot, people have different like slang or something, right? Like they say things like differently. Like what's an example of something? Oh, you know what? Some cool ones. So in the United States, for instance, we're a very big country, and within that we have a lot of big changes in like what people use for different words for things. So, for instance, what do you call like a Coca-Cola? What would you call that? You call that soda? Do you call that pop? What do you call that in Belize?
We just call it Coke.
You just call it Coke.
C-O-K-E.
Okay, cool. Yeah, here. Coke, soda.
In Canada, they call it pop. I think in England, call it soda.
Yeah, this is it. Yeah, this is a cool thing here, right? So in the South, they call it Coke. On the West Coast, they call it soda. East Coast, soda, and then like the Central, Midwest, or whatever, they call it pop.
I didn't know Americans also call it pop somewhere.
In the Midwest, they do. Yeah, it's like, yeah, here, what do you call soft drinks? It's soda, pop, Coke. Isn't this cool how it's like... Noise says it's Coke, end of. Yeah, okay. There's a...
It's just Coke, end of story.
Yeah. Well, I mean, but what I'm showing here is that like, you know, different people say different things, right? Depending on like where they are. And even within like physics, for instance, okay? There's kind of a difference between whether they will say VF or they'll just say V, or whether they'll say VI or they'll say V naught. Okay? So in this case, they're using V naught instead of VI, and they're just using V instead of VF. Right?
Okay.
It's important. It's important to know because, like, for instance, you may take physics with one teacher one year and they'll use one type of convention. And then when you take it again, when you go to college, they'll use a different convention. And then that may confuse you. So, like, it's good to be able to know what both are.
Okay.
Okay, so now that we have the equations in probably a form that you understand, okay, let's go back to what the actual question was, right? Which
Just
is...
have the regular-
All right, okay, we'll write the regular ones for you. It's okay, right here. The regular ones for you are.
I don't want to see this. I don't want to see this anymore. Get this off me.
He says, "No, I don't want to see it." No. Okay. Here, I think it's XF, right, is equal to XI plus VI T plus 1/2 AT squared, and then the other one that you guys know is that VF squared is equal to VI squared plus 2A, and then we say delta X. Right? Yeah, Noise. I literally just learned about SUVAT this year. Like, I didn't know it was called SUVAT.
Also, why do you have delta X there? Why do you have delta X?
Delta X means the change in position, okay? Which you could also write this as XF minus XI. Is that how Noise has been referring it to you? Has he been doing that? Does he do this?
I don't think he does it like that.
Yeah. This is the change in position is what it is. That's what delta X always means. Okay. You said
No,
X
I'm
was the
looking-
Oh, he just uses x. Oh, well, I don't know about that. You should say delta x, Noise. You shouldn't just say x is just displacement. X is technically position. Oh. Yeah. Okay. All right. So how are we going to use these equations, Ethan, to solve this?
Well, to figure it out, they have like they have some keywords in there like the distance, the acceleration, the speed, and the rest.
Good. Very good. All right. Cool. Yeah. Let's get that. Okay. So the distance, right, is 35.4, right?
Yeah.
Okay.
Which
So
would be x. It will be x for that.
technically it's delta x is what it is. Yes. If
Yeah.
we're just if we were just saying, yeah, this is delta x. 35.4 is equal to delta x. Noise says s. Yeah, okay, it's also s, I guess. Sure, if you want to say that. Okay. What else? What else do we have?
We have the rest that is assumed to be 0, since when you go to
Good.
save, you have 0.
Right. So, and what quantity is that? That's a velocity, right? But which velocity is that?
The rest is like the vi, the first velocity,
So we say vi is equal to 0.
and then the speed, which I can think is the vf, is
7.1, right?
oh right, yeah.
Good.
And and there's just one last key, which is the acceleration. I just don't know what that is.
Yeah, we're trying to determine the acceleration, okay? So that's A, and we don't know what that is, okay?
Okay, I see that.
So this is what I always like to do in physics. I like to see what variables do I have, what variables do I not have, which one am I looking for, and like which equation will help me out with that, right?
So I can see that it's the second one, since it has delta x. And that's the little only formula that has delta x.
Good. Yes. I mean, this has x in it as well. I could have written this as I could have gotten rid of this and said this was delta x, because it would be the same thing as xf minus xi. But you're right. Okay. Good. So we use the second formula. So then what do I do?
You plug in on what you have.
Good. Okay. So we're gonna plug things in, right? So we got 7.1 squared is equal to 0 squared plus 2a times 35.4. Okay.
And so the 0 squared can just go away.
Yeah. Goodbye. Goes away.
And then you gotta solve 7.1 squared.
Good. Yeah, we can do that. We can do that. You kind of need a calculator for. I can't really do 7.1 squared in my head.
Do all physics teachers allow you to use calculators?
No. You know, some classes you have to do everything algebraically, is what we call it, which means that you don't actually ever use numbers. You just use variables. Depends on the class. But in this case, you would need to use a calculator. The teacher would have to give you a calculator. But yeah, this would be 50.
Typically, a lot of classes won't even give you numbers.
Yeah.
So you have to write it in terms of variables.
Exactly. Yeah. Exactly.
Which is which would be a kind of a learning curve for a lot of people, because then you have to know which variables you do have. Like there are known variables and the unknown variables, which is takes a little bit of time to get you.
And also like which ones you're allowed to like use. Like when they say like, oh, put it in terms of the known variables, and you're like, wait, which ones do I actually know? You're like, which ones do I know? But yeah, okay, Ethan. All right, and then we multiply. I can do this one in my head. 2 times 35.4. That's just 70.8.
Which is a, and then you gotta divide them by 70.8, right?
Very good, dude. Very good. 7.8 divided by 70.8. And now we'll get our answer. Wait, where's my calculator? Calculator. There you go. So I'm going to do this divided by 70.8, right? And we get 0.712. That's kind of a small acceleration, honestly. 0.712. Okay.
That is so small.
0.712, and then what are the units for that?
Can I go back to that? Can I go back to the question?
Yep. That's for what the acceleration is.
It's meters per second, right?
That's velocity. Close. Meters per second is velocity.
Oh, Okay, hold on. Can I see that again? Let me see
Yeah.
that.
Uh-huh.
Hmm.
Yeah, do you see how it says
It's really-
speed is meters per second? Here's a
Yeah.
kind of a cool little learning moment here, Ethan. Okay, so acceleration is equal to what we say is the change in velocity over the change in time. Okay, it's how much velocity is changing in how much time.
Okay.
Velocity, right, is meters per second. What do we measure time in?
I don't know.
How do you usually measure time? Like,
It's in seconds, right?
yeah, good. Do you see how this is now meters per second divided by seconds?
Okay,
This is
but
the
how
same
does
thing.
that?
Well, the units for this would technically be meters per second, okay? But another way to write this is meters per
Meters?
second squared. Yes. You see that?
Yes, I do. I do. So how does that help with this answer?
Well, that's what the units are. The units are meters per second because remember we're meters per second squared because we're looking for an acceleration.
Okay.
Cool.
Yeah,
All
I
right.
think I got this concept down now.
Nice. Good job, Ethan. Yeah, next time we'll do some different questions, you know. It's good. It's good to repeat things to make sure you get it and whatnot. But always
But
good to learn new things.
also, what other physics questions could I ask them to get ahead?
Oh, there's so many here. Don't worry. I'm sure
What's the next
we
thing you could recommend me to do?
so we can talk about what's called projectile motion, which is the motion of things in the air, like the motion of like a ball going up and down. We can talk
I
about
thought of, hold on. I thought when I'm thinking of projectile movement, I'm thinking of a literal projectile.
good.
Like
Yeah, it is.
because it's like because sometimes when you do something with like a weapon, it throws like a beam, and that's a
Yes,
projectile. Like
correct. Yes,
a
like an arrow or a bullet or any. Those are all projectiles or a missile, right? And there's
even a shuriken.
there are a lot of cool physics concepts and equations that describe how those things move in the air. Pretty cool.
So even a shuriken can also be a projectile since you can throw it.
Yeah. Anything you can throw can become a projectile.
Okay.
Yeah. Projectile motion just means stuff in the air.
So I might as well search up on projectile movement and find a question about
Cool.
that.
Yeah. That's good. Yeah. Find something about that. We'll go over it. Or ask some stuff. I think Noise is teaching you kinematics in the Discord, so like he can give you a type of question and we can go over it during the stream.
Okay.
Cool. All right. Awesome.
Also, thanks for helping me get ahead before I get into physics.
You're very welcome. Very welcome. This is a great thing that we want to do like over the summer. While you guys are maybe probably bored at home, not going to school, is get you guys prepared for the next year coming up and get ahead a little bit. Because if you've already seen this stuff and you've kind of worked on it beforehand, when you actually have to do it later, it's gonna be super easy. You're gonna be the smartest kid in the class. It'll be great.
Yeah.
Yeah.
I also one thing is I saw Noise is teaching some complex numbers.
Uh-huh.
I thought about maybe also I might be doing one on Discord as well because
Cool.
complex numbers, like in the beginning of it, it's so easy to like understand it because it's like just getting used to what I is, how to work with it, and all that stuff.
Uh-huh.
And like the finding the I guess the angle, the magnitude.
Oh, in the complex plane, you mean?
Yeah.
Yeah.
And then I feel like it's just such a useful thing. Easy.
About that.
What's up, Hypatia?
Like they are teaching it in a really boring and wrong way. Like
You mean in regular classes they teach complex numbers?
yeah, like why do we have complex numbers? It's because
Yeah.
we find out there are certain equations that we cannot solve. There is
Yeah, we
this
can't take the
notion
square roots of negative numbers. It's illegal.
There's this notion of algebra closure, the fundamental theorem of algebra, and also we have number theoretic issues about embedding. So how would we detect if the like Well, that's
What
very
if like if complex numbers like even exist? Is that what you're saying?
well, not quite. Like for example, you can factor primes with Gaussian integers,
Okay.
and that is related to how a algebraic number field is embedded into a complex field.
Okay.
Or you can also talk about how complex numbers or the quaternions are the ways you can have division algebras. Basically, they are only for the like normed division algebras and stuff like that. Those
Mhm.
are the important ideas that led us to complex numbers. It's
Mhm.
not that without all of these motivations, you just tell people how like the angles or the modulus, like it doesn't make sense.
I see.
That's how you bore your students and
Yeah,
make them.
well, a lot of times, I guess students don't really have the knowledge, right, of the big whole, grand picture of mathematics and whatnot, and so they're just given these kind of these nuggets of like, oh, you want to square root a negative number? Here's how you do it, and then many years in the future, if you want to keep taking advanced math courses, you'll learn like why this is cool.
Well, that's why I was thinking about education reform is that
Sure.
why do we have to bore the students for so many years and then later, and then so many of them left us and then we teach some
And
of
yeah,
them.
and then we're not able to teach them the interesting stuff because they already got bored in the beginning. Is that what you're saying?
Yeah, or also, for example, like you're a physicist, you must know about the
Sure.
probability amplitude. That's also a good way to talk about a introduction,
Uh-huh.
a motivation for complex numbers.
Like
I-
for the wave equation, is that what you're talking about?
Yeah.
That
Like
one's also a philosophical question because there is not actually a rigorous way of saying like we need complex numbers. Like you can actually technically do quantum without complex numbers. It's just more inconvenient.
Mhm.
But I was reading about some papers as to why you need the thing, and it's just more convenient. Math works out a lot easier, but
It's just like, oh, it's
fundamentally,
easier.
I think you don't need to use complex numbers. So it would be I don't even know if that's a good motivation.
Oh, I see, because you're like, oh, well, it's actually just easier.
Yeah.
All right. We can go into that, and like maybe this would be a good thing to go over for like golden hour or something, Hypatia. If you want to like go into some more advanced things, or like even I do we'll talk after this. I do want to start like a kind of a more advanced math stream if you want to like take the lead on that, and then even I'm sure I would like learn some things. I know Ramton would be excited to also like learn like what these like higher level math things are.
I can also tell you about my thesis.
Sure, yeah, that would be cool.
Yeah, like it's pretty.
You're
cool.
in a PhD program right now, sorry, or you're in a master's program? I forget. Like what's?
I probably will finish this paper before I officially start my PhD program.
Oh wow. Okay. Oh, so this is like your personal thesis, I guess. It's not your
Well,
PhD thesis.
I have a informal advisor who is
Okay.
a really cool person.
Sure.
Right now, like US schools, they like so basically, they like the professors, the faculty members, they don't they like whatever they say doesn't count as much as in the European schools
Got you.
because administrations of the university they get the final say.
Right. There's all this
So,
hierarchy stuff. Yeah, I know.
Yeah, so despite I got some pretty big names behind my admission or
Cool.
support, it's still giving me so much trouble in terms of making it happen.
Yeah, it's an unfortunate we have the politics in our academia. Honestly, that's why I got out of academia because I was just like I'm done with the politics.
So toxic. Like if you're on Twitter, just yesterday there was a thing about a former scientist who was denied the tenureship because of sex and
Yeah.
basically there is this person on the committee who hates her.
Oh wow. It's just
And
like you're just not
then-
going to be tenured because I have a grudge against you, really.
And then when the person blow the whistle, you know what happened?
Yeah.
Like this person registered a anonymous email and starting to basically email email her like, you cannot fight the system. You are wrong. You are horrible. You are like basically this is the thing that, yeah, if you are not a tenured in a tenured position, you get fired for it. But
Yes.
they just
But
yeah,
I think
and then when the
this is
person-
a whole other discussion we should go into, like, because I think even tenured professors shouldn't be immune from being fired, because like there's a lot of stuff where I'm like, yo, bro, like they get tenure and then they're like, screw it, I can do whatever I want. I'm like, no, you shouldn't be able to just do whatever you want.
Yeah, I mean, if like, I guess what I would propose is that
We
if
need
you
term
want to
limits.
do whatever you want with your research, sure, you can do that.
But don't
but
don't exact
you
that
cannot
power over
use
other
this
people.
tenureship as a
Yes.
political toy. Like,
Yeah.
you cannot use it to influence like the administrative issues of
Right.
the university, and also you definitely cannot use it to abuse those like with, say, quote unquote less seniority than you.
Yeah, I agree.
Be it a new researcher in the field, be it a student.
Anything or something you don't agree
definitely
with.
cannot do that.
All good. All right, here, let's wrap up Teacup and Habib's questions, because we're getting a little late. Teacup, you here? What's up? Come to the stage, Teacup. Yep. Let me tag him again. I tagged him once, and then he was there. 1 second. Let me tag him again. Teacup. A good question. These are integrals. I think we're going to do U substitution here. I think, right?
Yeah,
Yeah.
it's a pretty quick one.
Yeah, exactly, right? Because e to the x. Yeah, where's Teacup? And then let's see, Habib, are you here? Are you here as well? I saw you have a question as well.
Yeah, we can do Habib's question first, I guess.
Yeah. What's up, Habib? Yeah, let's do yours, dude. I like these graphs. A lot of graph reading in the ACT, right? The ACT exam is all about like just reading graphs, because they have a science section, but it's not really science. It's like it's like science comprehension, I guess, is what it is. Did you ever take the ACT? Ramton?
Me?
Yeah.
No, I took the SAT.
Oh, okay, cool. What'd you get on your SAT? What was your 2 score? What was your math and verbal?
My math, I remember, was like 780 or something.
Oh, nice. There you go, yeah.
Yeah, I got 790. I was higher
790,
than-
dude. I got 720, dude. And I shouldn't have
You got
gotten 720.
One question wrong though, because
Yeah.
like a lot of times it's like weird how they mark it.
Yeah,
But yeah, I think
I should have had an 800.
English. I don't remember. I like botched my English. I was like getting wrecked because I was like, I spoke English for like 3 years now. I have to like fucking memorize.
Oh my god, no fuck. What?
Yeah,
Imagine Hypatia like going through that too, right? The English section is terrible.
Well, yeah, but to me, it's like I have to teach myself English because I need to escape China, I guess.
That's true. That's a good motivator. I gotta escape China or else the Communist Party's gonna come after me, so I might as well teach myself English. All right, Habib, here we go. The number of rooftops with solar panel installations in 5 cities is shown in the graph below. If the total number of installations is 27,500, what is an appropriate label for the vertical axis of the graph? Oh, okay, that's cool. How do you think we do this one, Habib? This is actually kind of a cool question. I like this. So they say here that the total number of installations is 27,500. Oh, Teacup's back. Cool. We'll do yours right after this, Teacup. Just stick around. Don't leave. I had to help my grandma. Oh, that's nice of you. You're a very good grandson. All right. So the total number is that. So the total means that like adding up all these things. Okay. So if we look at, for instance, city A, B, C, D, E, we see that A has like 9 of something, right? And then B has 5 of something. C has 6 of something. D has 4 of something, and E has 3.5. Divide by the total, yeah, it's kind of going to be that. Yeah, watch. Okay. So if I add all these up, right, this is going to be 14, 20, 24, This is 27.5. That's if these units were just 1, right? Okay. But I know I need my unit to be 27,500, okay? So what does that tell me that these units need to be? It is kind of like dividing by the total, right? Yeah. Does it need to be 100? No, not quite. Okay, because look, if this was times 100, right? If each unit was 100, then that moves the decimal place 2 places to the right. Okay, that becomes 2750. Oh, maybe that is right. No. Moves it. It's like that. That becomes just 2750. 1,000. Yes. Yeah. Exactly. Yeah. Because if this is 1,000, okay, now this decimal place moves 3 places. So that's 27.5, and then it goes 1, 2, 3, 4. Or sorry, 1, 2, 3, and then now we have our 27,500. So yeah, you want the number of installations in thousands. So it's just C. Yeah, good job. All right, nice job, PB. Last question. Let's do Teacup. Teacup. What's up? You here at the stage, Teacup? Gotcha. Hello, Teacup. Hello, Monsieur Teacup. Mike, is your mic working today?
Talking.
You're not used to talking?
I am talking.
Oh, I can hear you. Good. All right. Cool. All right. Okay. Cool. This is a cool integral question. Is what it is. Do you remember how to do integrals? Green's coming out, dude. I love that. Right? And with the Jeopardy music, I got them both combined there, dude. Because I love the Jeopardy music. Teacup!
Hello.
There you go. All right, he's back. Okay, what's up, Teacup? Teacup, let's go over like how to integrate things real basically, okay?
Yeah.
Okay, cool. Do you remember how to like do, for instance, like the integral of x dx? Do you remember this? Let's say let's like x to the 1, yeah.
It's like you raise the power and then divide it.
Good. Yeah, raise the power by 1, so that becomes x squared, and then you divide by the new power, so divide by 2, and that's plus c. Okay, that's what that would be, right?
Mm-hmm.
Cool. All right. This is called like the power rule for integrals, and this works when we have just things with powers. Okay, just straight polynomials is what we call them. Okay. There are some special integrals, however. Okay. Specifically the ones involving trigonometric functions. Okay. So
Definite.
this is an indefinite integral. This is correct. So let's remember. Do you remember what like the derivative of sine is? Do you remember that? Do you know what the derivative of sine is?
You mean cosine?
Good. Yes. Yeah. The derivative of sine is cosine. Okay.
Oh, okay.
Okay. And then the derivative of cosine is negative sine, is what we say. So it's actually kind of a cool thing here, right? This is taking the derivative of something, okay? Integrals are also technically called the antiderivative because it's like the backwards of a derivative, right?
Because you lower the power and then multiply.
Good. Yeah, you see that in the power rule. You see how they're opposite? Yeah, right, with the powers. That extends even further just to what we call like these special integrals, okay? So since the derivative of sine is cosine, we say that the integral of cosine is sine, okay?
Yes.
Okay. And by the same token here, the integral of negative sine of x is equal to cosine. But usually we don't like this negative here, so we're just going to put it over here. So I'm going to say that the integral of sine is negative cosine.
Mm-hmm.
Okay. All right, cool. These are important like integrals to know. Looking at this, right? I see I have the integral of sine, but then I got like some other garbage in there that kind of screws it up, right? This e to the x stuff, right?
Mm-hmm.
Like if this question was just the integral of sine of x dx, I could just use this, right? And it would just be negative cosine of x, okay? However, there is something inside that's messing it up. It's e to the x. Okay. When this happens, one trick we can use, Teacup, is called U substitution. Have you heard of that before?
Yeah, we use substitution, trig substitution.
Good. Yeah. So what U substitution means is I'm going to take whatever this like nasty stuff that I don't like, and I'm just going to call it U. All right? And we'll see what happens.
So
I'm gonna say that-
is equal to X
Exactly.
plus 500.
Well, U in this case is this ugly thing here. What is that ugly thing? What is it? We don't like it.
E to the
E to the x. Good. Very good. Okay, cool. Now, the next thing you do when you set your U, you need to then figure out what du is. Okay? So if u is e to the x, du is like the derivative of this. Okay? Do you know what the derivative of e to the x is? This is something Ramton just went over like really, really early on when we were doing the wave equation. No? Okay.
I don't, because I was helping my grandma like for 20 minutes.
It's okay. I'm glad you're helping your grandma. The derivative of e to the x is just e to the x.
Uh-oh. That's
Okay.
cheating.
I know. So we're going to write this as e to the x, and then dx is what technically you need to put here.
Yes.
Okay? The reason is like this kind of looks like, the same thing, like du dx is equal to e to the x, so I'm just moving the dx over. I'm going to write it like that. Okay?
Mm-hmm.
All right. Now what I'm going to do is I'm going to replace this stuff in here. Okay? So now I have the integral of sine, and I'm not going to write e to the x. So what am I going to write? Sine of what?
Hello.
Hey, you're good. You're good, Teacup. So instead of sine of e to the x, what are we going to write? Sine of what? Teacup. Did my mic go? I feel like, no, my mic's okay.
Yeah, your mic's fine.
Okay, good. Thank you. All right. Teacup. Oh, Teacup.
Hi, hello.
There you are. You're back. You're good, Teacup. You're good. We're almost done, Teacup. All right. So instead of sine of e to the x, I'm going to write sine of u. Okay?
Mm-hmm.
And then look at this e to the x dx. Where else do I see that in my stuff here? What is e to the x dx?
E to the x dx is... Wait, so the e to the x on both u and du.
It's just du. Do you see that? E to the x dx is the same as du?
Would that mean du is equal to dx?
That means du is equal to e to the x dx, okay? Or dx is equal to du over e to the x. Right? So this whole thing here, Teacup, right? I'm just going to write as du. So now this just becomes the integral of sine of u du. Okay? See how this is a much simpler integral to do?
Mm-hmm.
So what's the integral of sine of u du?
It would be... So if sine of x is equal to negative cosine, that would mean this would be negative cosine u du.
Negative just cosine of u, just like that. And then technically plus c. Everyone always gets mad at me for like leaving the c out. I'm like,
I don't like you now. You should have included the c goal. I'm gonna
whatever.
have to...
It's
I'm
plus the c.
revoking your...
My math degree.
Yeah, actually, no. You're being revoked from your life.
Please
You didn't pay your life taxes. Your free trial expired 18 years ago, and the
Oh,
IRS
no,
went
dude.
after you.
IRS is hopefully not after me. Yeah, so this is negative cosine of u, okay? But here's the key thing here, Teacup. Did my question here have anything to do with u's?
No.
Just x, right?
U substitution. Let's go.
Good. So we're going to plug this thing back in. So instead of negative cosine of u, this is going to be negative cosine of e to the x. And then plus c. And you are done.
I totally helped.
You
died
did.
quite-
You died quite a few times, but it's okay. You came back, and you stuck it through. And that's like the most important thing in life is perseverance. So, don't quit. No quitters here.
Hey guys, so we're doing population 1 today.
Bro, I played Population 1 actually. What was it? I think 2 nights ago. I had a really fun time with it. It's actually a very fun game.
Okay, so Gold is playing Population 1 for recess today.
I'm gonna play Warzone today, but
Against his will.
I will
Yes, no,
well, here's what I'll do. Here's what I'll do, Teacup. If no one joins me for Warzone, I'll play one match of Warzone. If no one joins me for Warzone, I'll play Population 1 with you. Is that cool?
Yay.
Okay, cool. All right. Thank you, everyone.
Population 1 now.
Yeah, you it's good. It's a fun game here. Let me close the stream real quick with people and then we'll
Bye.
talk. All right, thank you everyone for coming to Office Hours. Had a lot of fun learning with you guys. Awesome lecture about the wave equation and all the cool Hooke's law and pendulums. I learned a lot. That was cool. I had a good time with that.
Yeah, I'm
More
glad
questions
it-
like those are good. Yeah.
I feel like I really like teaching physics. Like,
Yes.
I like math as well, but like when it has applications or maybe some visual representation, it's like I like it a lot more.
I think that's what keeps it interesting. Honestly, you know, when people can see, like, at least in the physics sense, you know, when and even with the math sense, when people be like, oh, here's like what the math like actually does in the real world, I feel like that keeps people more engaged.
Yeah.
Yeah, and you have a very good way of teaching, Ramton, where like you go into a lot more of the math than I'm used to on physics. So it's cool because then I end up like actually learning stuff I didn't.
Yeah,
really know.
I think that was the incentive for me. I just wanted to learn more math so I could get better at physics.
Yeah, it's like the tools, right? You know, once you
Yeah.
have the tools, you can do more things. Yes, the leveling up. Are you around tomorrow, Ramton, for Golden Hour? You want to do the podcast? We haven't done it in like 2 or 3 weeks.
Most likely, yeah.
Okay.
Yeah,
Hi, Paige, are you around too?
I should be around. Most likely.
Okay.
Probably, I think.
Sweet, cool. Yeah. Well, I'll get the kids to ask some fun topic questions, and we'll talk. And I always have a fun time just discussing things. And then I gotta see. Hypatia, do you think I should like follow up with these grant people? I haven't heard anything from them. Do you think they would at least tell me like no, right? Or do we have to wait like 4 weeks?
I mean, it's only July, so
I know.
mm,
It's only
How
July.
How long ago did you guys apply?
We submitted it on the 21st, I think, Hypatia, right?
Yeah.
Yeah, we submitted on the 21st.
I think it's too early. I would
I-
say like give it like a month or two, honestly.
Okay, I'll give it a
they
month.
said they're going to distribute the fund at the end of September. So
Oh shit! All right,
yeah,
that's a long time.
like, at least they will give you something.
Yeah, I'll
like,
tell my landlord to just chill.
Might not be the full amount, but it will be something to start with.
I'll take anything. I'll take anything at this point, honestly. You know, because you know,
will give you 1
I
cent.
I think a big thing, especially with any sort of like nonprofit funding and whatnot, is people want to see that somebody has given you money first before they'll give you money. And if we haven't had anyone big give us money yet, I that first seed pot I know will make things a lot easier. You know, we get like more legitimacy, I guess.
Gold, if I donate you 1 cent, can I triple my investment to be 3 cents?
Yes,
W.
W, 3 cents every time.
Yeah, I'll mail it to you right now.
Okay, thank you. It would cost you more than 3 cents to mail it to me. It's like I think the
Man,
minimum. I
fine.
think the minimum
It's a
on
lot
like
of
is like 4 or 5 cents these days.
Oh, dang.
No, it's like 40 cents, 40 or 50 cents. Anyways,
Here,
okay.
I'll give you 100.
Give me $1. Yeah. Well, I already got $2.50 due to Habib giving me a sub. I appreciate that. Or Jeffy Bezos is gonna give me $2.50 through it. But
Jeff Bezos is coming for you.
I know. Oh, he is.
Same
Okay.
as the iOS.
Let's not wish those things. Knock on wood. All right. Next stream is gonna be tomorrow, golden hour, same time, same place. It'll be more open-ended. We'll talk about some cool stuff. You know, I always just love to chit-chat about the world. There's a lot that's been going on in the last 2 or 3 weeks, so I'm sure we have a lot to talk about. If you haven't joined our Discord yet, please do. It's just discord.actual.education. Well, that one doesn't work right now because I need to get us 3 more boosts on the server. So yeah, if anyone has Nitro and they want to boost the server, we need 3 more.
You know,
I'll-
if you
I'll-
give me
I'll-
some Nitro.
Exactly. I'll just probably give away Nitro to some kids and then they'll boost the server, and so like it'll be back.
I don't know. If you give it to me, I'll boost the server, but I don't know about anyone else.
Okay, we'll see. All right. And then the next office hours will be Friday, an hour later at 5 p.m. But otherwise, Okay, cool. If you want to come play Warzone with us, we're gonna do that on Actual Gaming. So if you're in the Twitch, just stay in. It'll take you there. If you're in the Discord and you want to come play with us, that'll be in the Recess channel below.
Yeah,
Otherwise,
I can play this. Like,
can you, Hypatia? Can you play this game? You got something right to play it?
I didn't figure out how to play it, but I think it can run it. So yeah.
Okay,
Oh, dang.
sick. We'll figure it
I mean, no
out.
popping.
We're gonna figure it out. Well, I'll play at least 1 or 2 with Hypatia. We'll see what happens. Okay, cool. All right.
Yeah,
thank-
so-
It's in Modern Warfare 2 plus Warzone 2, or just
Warzone 2.
COD?
It's just
Okay.
Warzone 2. You got it. All right. Cool. All right. Thank you everyone for coming by today. Had a lot of fun. We'll see you tomorrow.
Do you guys
Enjoyed-
play Warzone 2? Is that the one?
Warzone 1 doesn't even exist anymore. They actually just took down the servers.
Okay.
Yeah.
I
It's
guess
just
I'll
Warzone 2.
install that and then join.
Yeah. Yeah. Try. Yeah. It's a big download, so it might be till next week. But yes.
Yeah. That's what I'm saying. Like until
Okay.
next time.
Okay. Cool.
Like I'll
Yeah.
just download it overnight tonight.
Perfect. Yeah. We'll play. It's a fun
that's
game. to play.
Another good perk about this cloud gaming is that I never need to download it.
Yeah, dude, that is fun. You don't ever have to actually like take up all the hard drive space.